Hi everyone, Samar here and welcome back to Go DevOps. Today we're focusing on containers networking. So how do containers actually communicate with each other and of course with the outside world. So let's get started. So let's start with a simple analogy. So imagine a city. Each apartment represents a container and containers are isolated just like apartments in a building. For communication to happen, two things are required. So first, roads. So these represent the network and allow movement between containers. And second, each apartment needs a unique address. So in networking, this is going to be an IP address. And every container is assigned an IP address, which allows to be identified and reached. And without roads, there's no communication. And without an address, there's no way to know where to send the data. So container networking is what connects these isolated units, so apartments, and enables communication between them. So what exactly is container networking? So it's actually the way containers connect to each other, to other services, and to the outside world. Even though multiple containers run on the same host, each one gets its own isolated view of the network. So this isolation is made possible using something called a network namespace. And when a container is created, the runtime sets up a dedicated network namespace for it. And inside that namespace, the container has its own container interface, its own IP address, its own routing table, and its own firewall rules. And at the same time, all of this is built on top of the host Linux network stack. So in practice, containers share the same underlying infrastructure, but behave like independent machines on the network, so without interfering with each other's traffic. Now let's break down the main building blocks of a container network. So first, every container is connected through a virtual network interface. You can think of it like an ETH0 inside the container that links it to the network. And these interfaces are attached to virtual networks created by the runtime. And on a single host, this is typically a bridge network. And across multiple hosts, it can be an overlay network. So each container then gets its own IP address from an internal subnet, so services can communicate with each other in a predictable way. And to move traffic, we rely on routing tables and gateways, and they decide how packets travel between containers across hosts or out to external systems. And when you need to expose a service, port mappings are used to connect a port on the host to a port inside the container, while keeping everything else isolated. And for communication between services, DNS-based discovery allows containers to use names instead of hard-coded IP addresses. And on top of that, network policies and firewall rules control who is allowed to talk to whom. And finally, all of this is configured and managed automatically by container runtime and orchestrators, so you don't have to handle each piece manually. Before going deeper, it's important to know that there are several ways to configure container networking. In practice, there are 5 main modes you'll come across, and we're going to go through them one by one, starting with the simplest. So the first mode is the none mode, and in this setup, networking is completely disabled. So the container does not have any external network interface, and it means the container cannot communicate with other containers and it cannot reach the outside world. So this is mainly used for very controlled workloads like batch jobs or isolated processes where network access is not required at all. So everything the application needs must already be available locally, so either inside the container or through the host file system. The second mode is bridge mode. So in this setup, containers are connected to a virtual bridge created on the host. So you can think of this bridge as an internal network that allows containers on the same machine to communicate with each other. And this is the default mode in many environments because it provides a good balance between connectivity and isolation. Containers can freely talk to each other inside this virtual network, but they are not directly exposed to the outside world. So if you want to make a service accessible, you need to use port mapping. And this means you explicitly connect a port on the host to a port inside the container, and only those selected services become reachable from outside. The third mode is host mode. In this case, the container does not use a separate virtual network. Instead, it directly shares the host network stack. That means it uses the same network interfaces and the same ports as the host machine. So there is no network isolation here. And from a networking perspective, the container behaves almost like a process running directly on the host. So the advantage here is that there's no extra layer, so networking is more direct, but the trade-off is that you lose isolation, especially when it comes to port usage and network separation. So this mode is typically used when you need direct access to the host network and you're okay with that reduced level of isolation. The next mode is overlay mode. So this is where things move beyond a single machine. So in overlay networking, containers running on different hosts are connected through a virtual network built on top of the existing physical infrastructure. So even though the containers are on separate machines, the network makes them behave as if they are parts of the same environment. So this becomes essential when you scale applications across a cluster of nodes, especially in clouds or a distributed system. From the container's point of view, it doesn't matter where it is running. So it can communicate with other containers as if they were on the same local network or subnet. And the final mode is the MAC-VLAN mode. And in this setup, each container is assigned its own MAC address. So from the perspective of the physical network, each container looks like an independent device, just like a physical machine. So this gives a very low level and direct integration with the existing network infrastructure. It is really useful when you need strict IP management or when working with systems that expect traditional network behavior, such as legacy devices or network policies that treat every machine as a full host. So this mode is really used when containers need to behave as first-class network devices on the physical network. Now let's connect everything and see how container networking actually works step by step. So first, when a container starts, the runtime creates a network namespace for it. And this gives the container its own isolated network environment with its own loopback interface and virtual network devices. Second, that namespace is wired to the host network using a network plugin, usually following the CNI standard. And this is done through a virtual Ethernet pair that connects the container's namespace to a network driver on the host, like a bridge or another networking implementation. Third, the network configuration is applied. So this includes assigning an IP address, setting up routes, and configuring DNS. So the container can properly communicate with other services. And finally, the container gains full network connectivity. So at this point, it behaves like a normal node on the network. So it is able to communicate with other containers and external systems, of course, depending on the rules and routing policies that were in place. So in simple terms, it goes from isolation to connection to a fully functioning network participant. To make all of this work in a consistent way, we rely on a standard called CNI, so Container Network Interface, and it defines how container runtimes should configure networking, regardless of the platform or the underlying infrastructure. So in practice, the runtime sends a JSON configuration to a CNI plugin, and that plugin is responsible for setting up the container network, so assigning IP addresses, configuring routes, and applying DNS settings, and then returning the result back to the runtime. So this standard is especially important in orchestration systems like Kubernetes, because it allows containers to be created, moved, or scaled across multiple hosts while keeping networking consistent and seamless. So what should you take away from this video? First, container networking is what allows containers to communicate while still staying isolated at the system level. Under the hood, each container gets its own network namespace with its own interface, its root, and its rules. And all of this is built on top of the host network stack. We also saw the main networking modes, so the none for full isolation, the bridge for single host communication, host for direct access to the host network, overlay for multi-host communication, and MAC-VLAN for exposing containers as full network devices. And finally, standards like CNI make all of this work consistently across tools and environments, especially in orchestration systems. So the key idea is simple. Containers may look lightweight, but their networking model is a full system underneath. And once you understand that, everything else starts to make sense. So thank you for watching, and I hope this video was helpful for you. Don't forget to give it a thumbs up, and see you for the next video about the basic life cycle of a container. Thank you. Bye.